We're here looking at the AMM contract, and I've got Marcus here with me,
Mm-hmm.
and we're just
Yo.
gonna talk about how it works and try to provide a better understanding of like Hoon smart contracts, Uqbar smart contracts. So so yeah, this is a pretty simple contract. All in all, with the library file and then the actual contract, we're looking at like 400 lines of code. That includes a lot of commented out stuff. So yeah, should be fairly tractable for people. Yeah, so let's start with some of the type definitions here. And yeah, Marcus, just feel free to chime in with comments or questions as we go through this. Um,
Mm-hmm.
so so right off the bat, yeah, you can see like I don't have the protocol fee activated. So if you're familiar with like AMMs, you could set it up such that every swap engenders a small protocol fee. We don't have that activated right now. So most of the commented out code is related to that. Um, but we do have a trading fee. We do have a trading fee. So this is measured in basis points because it's much more convenient to work with whole numbers, natural numbers, no floating point math involved. So yeah, we just do trading fee 30 basis points, which means 0.3%, and that's hard coded.
Mm-hmm.
We also have a fungible contract ID hard coded here. Uh, the reason for this is that when you create a pool in an AMM, you mint liquidity tokens, right? Those are how you redeem and get back your underlying asset that you're providing liquidity with. And because we, as the AMM contract, are minting a token, we need to have a contract that we can mint through. And that's, we use the generic fungible contract. And that code is visible under fungible.hoon in the Uqbar core repo. So yeah,
Mm-hmm.
we've got some
Nice.
stuff commented out related to a treasury token. Can ignore that. Here's a convenient definition of like 18 decimals because this is one full token. And this is useful for the math around um, division specifically for when we calculate like, you know, dividing one token by another token. This is like what gets us precision to the 18th decimal point. We multiply things by this. Um, yeah, so now we're into the real data types. Um, so we've got, these are the key data types. First, we've got the pool. Pool consists of two tokens, an amount of liquidity shares, and then the ID of the liquidity token metadata. And this lets the AMM contract access um, that liquidity token that gets minted and burned when people add and then redeem liquidity from the pool, right? Um,
Some, Something that when in Uqbar, like data and contracts are separated and you have all these IDs either being data or contracts. Something that confused me a bit that I might clarify for new people is that like when you do anything with tokens and like tokens in general, the fungible token contract is just a contract that deploys new data items of like specific fungibles. So when you pass around the metadata of a token, that's just another data item that describes basically a fund. It has a supply, it has a cap, and then it doesn't point to, but it's the holder of a bunch of other data items that are specific accounts, basically.
right,
Um,
exactly. Yeah.
so,
So
so yeah.
yeah, so normally in a normal like Solidity smart contract, you're really concerned with contract IDs, right?
Hmm.
Um,
Yeah.
but in this model, we, yeah, we have token accounts, right, which live as like sort of their own items on chain. Now they're controlled by a contract ID, but accessing a specific account on chain requires knowledge of um, the metadata for that token. Because yeah,
Hmm.
yeah. So like that's a good point, Mark. It's like these contracts are often actually generic, right? So like just knowing the contract ID in a vacuum doesn't give you enough information to know specifically what token it's talking about, because in the fungible token standard, the contract is generic, can launch multiple tokens through it.
And even though we do require knowledge about many things, you'll see this afterwards in the like Golap and other places, is that even though you do require knowledge, you can look at the contract and see how these data items are hashed. For example, account items. So then if you know an address and you know token metadata, you can just kind of hash it yourself, even outside of a contract context, and just scry your local indexer or someone else's, and basically find out what's going on chain.
Right. Yeah, that's really useful, and there's a lot of that happening inside the contract logic. Um, so yeah, the next stuff is just helpful types for like contract actions. We have the token arguments. This is again like giving us information so we can manipulate the tokens that are going to be going into and out of pools. And then we have a token account data type, which is actually copied directly from the fungible token contract. So a token account has a balance, allowances that let other addresses spend tokens on your behalf, an ID of the metadata for that token, and then a set of nonces. And these nonces are sort of a funky little feature that let you do gasless allowances and gasless signing with your tokens. So that's a bit of trivia there. Yeah, so now let's go into the actions. This is a data type you're going to see in basically every Uqbar smart contract. Every contract has a type that's a union of many types tagged by a head atom. That's what these things are. Labels, essentially, that let you have multiple actions living within this one data type, so that when somebody performs a transaction, you can mold the call data to this type and then manipulate it with ease. So yeah, we've got a bunch of actions here. We've got start pool, and these are fairly self-explanatory. I think they're well labeled. I would hope. Start pool, do a swap, add liquidity, remove liquidity, and then a special handler for on push, because when somebody does a push from a token contract, we want to handle that, and that's a useful feature that we can explain when we get into the code. This is for if we had a protocol fee, so that's not important. And then we have one helper function down here that lets us get the salt of a pool that we've created, so that we can more easily access that account, so to speak.
This is hashing, basically.
Yeah. Okay, so yeah, with these 4 key actions, and on push basically is something that lets you take an action directly from the token contract, instead of forcing the swapper, specifically the person doing the swap, to set an allowance first and then perform a swap. We can do that all in one smooth action and just take that from the token contract and then mold this call data and do a swap for them. So that's really convenient. A nice feature there. Oh yeah, it's described here in this comment.
This enables you to do swaps like immediately. You send the swap call data to the fungible token. That one just makes an allowance, sends the call data onwards, and if something fails in the swap, like the whole thing fails. Nothing gets reinstated.
Okay, great. So let's go into the contract itself. And in fact, we can keep these types next to us so that for reference, right? That's helpful.
Nice.
Keep that right there. So now we're in the contract, and let's just literally go through this line by line, because I want people who are totally unfamiliar with Uqbar smart contracts to be able to follow. Some prerequisite knowledge of Hoon is assumed. Yeah, so first we do our imports. We import the smart standard library, which is just the basic Hoon.Hoon, like Hoon standard library, minus a few things plus a few things, and the things we've added are like helper functions and associated stuff specifically for building contracts. So contract data types. If you don't recognize a type that either we didn't go over in the library or you don't know from regular standard Hoon, it probably lives in smart.hoon. Um,
Hmm.
so yeah, we also import our library right here. So yeah, contracts have a very basic structure. Here's the structure in its entirety. They have a write arm, they have a read arm, and they both live in a door that takes in context. Right?
Hmm.
Context is chain context. Uh, I'll just show this right away. This is in smart.hoon. It contains the ID of this contract that we're in right now. It contains the caller information, the batch number we're on, the ETH block that the sequencers most recently made us aware of, and the town ID that we're running on right now. So
Hmm.
yeah, pretty straightforward. Um,
Something to note, or like two quick notes, is like this contract it'll only do one write arm, one read arm, nothing else. Like if you're like me and you want to make a very very compact, nice contract, and you try to put like a lustblock type definition in there somewhere, that won't work. That will crash upon execution. Make a
yeah,
lib file. They're very similar to serve files in Hoon anyway. It's like a nice separation, and also if there is some function that you don't see in your library or something else, you can literally, yeah, just go to like smart.hoon or just search your whole like directory and you'll most likely find it and it will most likely make some kind of sense.
yeah, and of course you can import multiple libraries here as
Hmm.
well. Um, so yeah, I mean the write arm and the read arm. The reason we're restricting to that is because it lets us basically run transactions through contracts on the fly with no need to compile the contract every time, because we basically just like assert that the contract matches this shape, and then we can basically run it as raw knock directly. So that's
Hmm.
it's very fast. It's also
Nice.
yeah, it's easy to use, and it's all you ever want to do with a contract. Contracts are fundamentally very like, constrained things.
Hmm.
Yeah, okay, so we take in to our right arm, we take in this action type, and that's just straight up this. So now from here on forward, we know what we're dealing with. The user
Hmm.
has given us one of these things in a transaction. The contract execution engine has already signed, verified all of the requisite things that the user is paying for gas. The user signed this transaction with their public key. We're all good to go. We don't need to worry about any of that. And what we want to return here is a pair of two things: a list of calls, which is what a quip call diff tells us. You'll
Hmm.
recognize this from like a gall on poke, where you have quip card this, quip card state, right? This is very similar.
Hmm.
So we have calls, which are continuation calls, and then we have a diff, which are actual side effects to place on chain, in the form of items created, modified, burned. Um, yeah, issued, modified, burned. So from here we're just going to branch on what action we get. And Marcus, what do you think? Should we go? What's the easiest action to start with here? Do you have any thoughts on that?
Maybe I don't know, swap or add
Yeah,
it depends. Start pool has some, yeah, yeah.
I guess we
Uh,
should start pool,
it just
right?
start, yeah,
Yeah.
yeah.
Let's go chronologically, because the first thing you're gonna need to do is have a pool, and it'll make more sense to modify that pool.
Hmm.
Um, yeah, so we go to start pool here, and what we're trying to do with this action is literally just create a new pool on chain with the input tokens that the user provided, right? They're actually going to be sort of seeding this pool with liquidity, and we're going to mint them liquidity shares based on what they added to the pool, right?
Mm.
So first thing we do here is calculate the amount of liquidity shares. And by the way, all of this logic is copied directly from Uniswap v2. All of
Yeah.
the math here is like, just a as good as we can of a reproduction of what's going on there. So yeah. Um,
Mm-hmm.
so yeah, the white paper for Uniswap notes that you should burn an infinitesimal amount of liquidity shares right off the bat, because otherwise you can end up in a situation where basically like all but an infinitesimal amount of liquidity shares exist, and so you get very very large numbers of value because it's a very small divisor, and it distorts
Mm.
the value of liquidity shares,
Mm.
and you can prevent this by just burning a tiny amount. Now remember that like all of the numbers here, all of the integer numbers in this contract are to the 18 decimal point value.
Mm-hmm.
So this, in your head, you should think about this 1000 as 1000 out of 1, which is, this large.
Mm-hmm.
This is 18 decimal points, right? And
Yes.
1000 is right here. So we're looking at really 0.00000000000000001 tokens. Yeah. Yeah.
This is the reason for certain, if you deploy a fungible token and you want to send it to your friends and you think you're deploying a lot and you mess up, miscalculate, and all of a sudden your tiny amount of token is worth a lot of testnet SIGs.
Right.
Uh,
Right. So yeah, so the actual equation here is we just, to get the liquidity shares, we multiply the two token values and take the square root. Um,
mm-hmm.
so yeah, pretty straightforward. And that's the Uniswap formula, and it works. Okay, so next up, we're actually going to be like creating an item on chain, and items all have salts, and the salt is what makes the item ID like deterministic and unique. So yeah, so we'll use that helper function, and we'll calculate the salt by just concatenating the symbol values of the two tokens in the metadata. So that's pretty straightforward.
Mm-hmm.
And
This is
yeah.
and this is the reason why you also like, oh, if there's one pool already, well, pools can differ, but like, oh, you, there's a certain uniqueness to deploying these.
Exactly, exactly. And this is like important to note because like this is the kind of this is the probably the hardest part about writing contracts, is like coming up with getting that piece of data that's going to make your protocol sort of these items unique, right? And like sort of like
Mm-hmm.
perfectly scoped in their uniqueness, right? So here we're concatenating the metadata IDs of the two tokens because that's like that one unique piece that determines what token you're actually operating on. So this enforces that every single pool that you could make is exactly unique, but
Mm-hmm.
there's only one possible pool for every token pair. And that's why you can
For
yeah,
for this contract, every item also has a source and a holder.
exactly.
So another contract could do the exact same, get pools, like deploy
Yeah,
pools with the same salts, but be different.
exactly. Yeah. Um, yeah, so now we this is literally just grabbing the names of the tokens from their metadata because we want
Mm-hmm.
to label the pool correctly. So we take the metadata IDs that the users provided for the token. We scry the chain state, so we just find the item that corresponds to this value, this ID value, and we say we need it, right? This returns a unit. We say we need the unit. If not, the contract crashes. This enforces that like the token metadata actually exists.
Mm-hmm.
We do some funky stuff to grab the contract value for the token and also the symbol value for the token. So this is going to be, like a symbol is going to be like Ziggs, right?
Mm-hmm.
Or like that's the name of the
The
token.
the funky stuff might look funky in the beginning, but all you're doing is like on line 21, you assert that like the head of the item you have has a yes, like a boolean true in front of it,
Right.
because each item is like either it has yes in front. If it's a yes, then it's a data item. If it has a no, then it's a contract. And the WhatSig populates molds the data so you can access like source.p.a in the next line.
Right. We're just doing,
Otherwise, you
yeah.
Yeah, you'll see that a lot.
We're doing type
Uh,
refinement here, right? So we're just
yes.
taking this like very unrefined type and we're refining it down to like the metadata type that we know about so that we can grab the symbol out. Um,
Hmm.
and we do this for both of the tokens. So this code is duplicated here, A and B, right? Token A, token B. And now we finally do the interesting stuff where we produce the results. Um, so we produce a metadata ID for the liquidity token that we're about to mint because it's a new token, right?
Hmm.
So we make an ID for a new token metadata. Um, we're basically pre-calculating this because like we're actually going to send over this information over to the fungible contract. The fungible contract is what's actually going to mint this item on chain, right? But
Hmm.
we're pre-calculating it so that we can insert it into our state so we can access it later when people do
Hmm.
swaps. Um, so
And
yeah,
these two are like dependent on each other. So even though this comes a few lines after, but when we add this like specific liquid token metadata to our state, and we say like, oh, this item is now minted, this is a new one, and then we also pass a call to the fungible, like, hey, mint this item that I already put in my state. If the fungible contract for some reason the call reverts, say you already minted that one, or something else,
right,
probably only that one, then the whole thing reverts. So you don't put it in the state. So you don't.
right.
You have this nice
Yeah,
guarantee.
that's a very important property of these smart contracts. You can be very like sort of like I don't want to say cavalier, but like you can do a lot of stuff with the assumption that subsequent code is going to execute because the way a transaction is performed on chain, like it either all works or it all fails. So
Mm-hmm.
you can basically assume things are going to succeed in the future, and if they fail, like you're not getting there's no like re-entrancy in Uqbar. So
Very
that's
nice.
that's nice. Yeah, so okay, so we create an actual pool. So this is we're just going to put this data type, this pool data type into an item and we're going to put it on chain so that we can access it later. So you see here we're taking the values from token A and token B, the liquidity shares that we calculated, and then we produce one of these data objects right here. So data
Mm-hmm.
has an ID. Um, we are the source. We are the holder. The town is the town. The salt we calculated is the salt, and then we have the pool data. Um,
Mm-hmm.
and then we issue our result. So result is just a diff, right? So our diff has four pieces. We're only using one of them. This is changed, modified pieces of data.
Mm-hmm.
These are issued pieces of data. So each of these are a list, right? We have one
Mm-hmm.
issued piece of data. We have zero burned pieces of data, and then we have zero events outputted. So we should probably be emitting events here. We haven't
Yeah.
included that in the contract yet, but like this is where you would put an event that could be readable in an event stream. So we would
Mm-hmm.
put an event here that says X pool was created, right, with Y amount of liquidity. That would be helpful.
Mm-hmm.
So after our diff, we insert a list of continuation calls. So these will be fairly self-explanatory. Like you could go into a lot of detail by going over to the fungible contract and seeing what each of these things do, but I think it's sufficient to describe them here. So we've got three side effects, right? Or three continuations. We've got one is take as many tokens of token A that the user wanted to seed this liquidity pool with. So take the tokens and put them in our ownership, right? We can
Mm-hmm.
take because the user is assumed to have granted us an allowance. If they hadn't granted us an allowance for both token A and token B, this entire transaction will fail. Um,
Mm-hmm.
so take token A, take token B, and then deploy a liquidity token. So all of these are going to fungible token contracts. The actual contract address is determined by the user provided tokens, right? They could be at any contract address. But for minting the liquidity token, we use our fungible contract, which is that hard coded contract ID over here. Um,
Mm-hmm.
So yeah, we mint a new liquidity token. We label it as what it is, right? It's a liquidity token of symbol A, symbol B. It's got its own symbol, right? Um, we are the sole minter, and then we immediately issue the number of liquidity shares that we've calculated for the user to their address, right? That's just like all very straightforward. And yeah, and if any of these fail, the entire transaction will fail. So these are traversed in a depth first manner. So the initial
Mhm.
transaction is to the AMM, and then the AMM does 3 transactions in sequence: take, deploy. If any of them fail, all of them fail,
Nice.
including this top level one. So that's start pool. Um,
Hmm.
that's everything. So pretty
You
clean.
could probably rewrite the two takes, the allowances, which one does need. You can't do on push there because you need two allowances with like signatures and passing them and kind of like on
Yeah,
pull arm that also exists in the fungible and Ziggs contracts.
yeah, that
Um,
would be a gas efficient way to change that. So you could pre-commit to spending those, and then you could have, well, yeah, yeah, that makes sense. That makes sense. Yeah,
mhm.
you could initiate the start pool with an on pull to get rid of an action there.
Hmm.
Um,
This will make more sense as we go to the swap, which is the next one. This
yeah,
kind of happens here.
yeah, okay. So I don't know. Do you want to talk through swap, Marcus?
Sure. The like the first line is just like the same as last time, just like expose the types of the action. So they'll need to explicitly say dot act every time. Then you do the same thing as before. You scry the state, you get a unit back, need, but then you also husk that into the pool data type. So husk takes a type, an item, and a unit holder and a unit source. So in this case, we and it's going to try to mold that data item and then check like mimic it basically, and then also check for the source and the holder. So in this case, we look for a pool. We check for the noun in this specific item is both the pool type like we have in the lib file, and we also check for if the source is this contract and the holder is this contract. Um, yeah, and we do a little bit of math magic with a fee that
Yep.
um, and then basically like we take and check for like which side should go to which side. Like pools are from token A to token B, but you might have inputted like, oh, token B to token A, and we check that those all are correct. Uh, then we assert that this pool actually is this pool, that we can do this. Um, and yeah, then we have like constant product formula basically at this point, which is
Yep.
just, you can look it up. You take this basically is a, anyway, you've seen this around. If you haven't, it's a interesting Vitalik type like function. You just multiply the total amounts of tokens you have in your pool, and whatever you do with the swap, the total should stay the same. So what this in effect does is make it very expensive to like disbalance the pool very much. If you've seen the front end for the AMM, you'll see like crazy price impact functions, as you see with like low liquidity tokens in Uniswap too. This is maybe not the optimal way to swap, but yeah, so that makes it expensive. So we calculate that, kind of get a minimum amount of received, and you'll see this too. Like when you pass in, you'll give like, hey, I want at least this much because there's some slippage. Um,
Right.
yeah, then we assert that that is actually what we get. If not, then it just crashes.
Yeah,
Um,
so this allows the user to set a value that if the constant product formula doesn't give them the minimum amount of tokens that they expected to receive, it basically just aborts the transaction.
mhm.
Yeah.
Yeah, which yeah. Um, and then we have a tisk call, which just changes some legs in the subject. So In this case, we change the liquidity token basically of what's going on. Uh,
Yep.
yeah.
Well, so
Um,
this is actually this is the liquidity in the pool, right? So
yeah,
we're
that's, yeah.
we're literally saying like if the pool had 100 of token A and 200 of
Hmm.
token B and you swapped, one token A to get two token B, right?
Hmm.
We're just subtracting those values, right? We're just adding the new, yeah, we're calculating the new amount of tokens in the pool because we're going to give the payment, we're going to take the payment from you and we're going to give the received amount to you. So this is like
Mm.
just making sure the pool stays in line.
Oh, okay. But
Yeah.
we're modifying the swap input here, and then we go down, and then we have the pool data that we like spread out before. That one had a noun, and
Right.
then we change pool. We change the token A to swap input, token B to swap output,
Exactly.
or the vice versa around, depending on which way we want to do this,
Exactly.
or which way the
Exactly.
token goes.
So
And
we
yeah, same.
yeah.
Sorry.
No, no. I mean, I was just gonna say we end up with like one updated pool, right? That's our
Hmm.
only diff here. Um,
Hmm.
but
Yeah.
then we have some continuation calls. So
Yeah. So this, yeah, the same thing. You have a take, which assumes an allowance. Um, you have a take from wait, where does this take go? So we have, oh yeah, so you define a contract where this is going. Either it's say ZIGs or a fungible in most cases. So we take some tokens from there, and then we give to who's going to receive. You take and you give some. You get
yep,
some, you give some.
yep,
But like in the case, we'll see that later. But like the on push arm that's written here, maybe not the greatest time to talk about that. But in essence, when you only have one take, you only have one allowance you need for some operations, which often is the case. You want to take something and do something with that token. Um, in this case, this can actually be a continuation call already. So the first thing that happens is I call the push function on the fungible because I want to switch the fungible uh, token to some ETH or something else. The only thing that does is change the state in the fungible token, adds like an allowance to this contract, and then makes a continuation call to this contract. Uh, what this does is we go here. We only support swap and remove liquidity currently because they only require one approval. We take that call data that the fungible contract passed us. We check some things if it's like swap or remove liquidity, and then we basically we call ourselves this action with this. So,
exactly.
for example, if it's swap, then it goes back to swap, and then we make another continuation call to that same fungible. So you can see how this like back and forth goes in a cool way with the allowances, and while like keeping state and effects like kind of coolly together. Like it's all, if something
Exactly.
fails, everything fails. It's like
Exactly.
nice and nice and solid
Yeah.
somehow.
Yeah, so this is a really convenient like function because uh, we let the user turn what would be two separate transactions into one transaction, right? Where they set their allowance for the token and they can set it to exactly the amount they want to spend at that time, right? And then
Mm-hmm.
they can execute a push to this contract through their token contract. And then we get to just literally do a bit of recursion, modify the subject, and take the call data in their push and apply it to our either swap or remove liquidity arm. That's what
Mm-hmm.
this buck does, right? This cash sign. It goes back
Mm-hmm.
up to the top level function, but with these pieces of the subject modified. So we take new call
Mm-hmm.
data and then we actually like insert the caller to be the person who initiated that push to their token contract. And then we get to act as though they were the caller up here in swap, right? Really, really clean, really, really convenient. So yeah,
Mm-hmm.
probably needs auditing. but
Yeah,
but
that's
I'm
changing the call data
yeah.
like from
Well,
part can
it's
be a bit.
it's definitely like a scary thing, right? Like it's definitely
Yeah.
like it feels very risky. A formal audit of this code would be nice. I feel pretty confident though in the overall architecture of what we're doing. There might be,
Hmm.
you know, missing assertions somewhere, but like the overall architecture is valid. Um,
Hmm.
so yeah, so that's swapping. Next, we've got like add and remove liquidity. These are, but I think we only really need to go through one of
Yeah.
them because they're fairly similar. Because basically, like high level, right? With add liquidity, you are depositing a bit. Well, you're depositing some of token A and some of token B, right? And we have a ratio at which that's, well, you can deposit at any ratio, but you're
Yeah.
you're really gonna want to deposit at the existing ratio of the pool because otherwise you're setting yourself up for to have your liquidity tokens arbitraged away. These are just like fundamentals of constant product formula swaps. So yeah, add
Hmm.
liquidity. We're putting some liquidity in the pool. The contract is going to mint us liquidity tokens. Remove liquidity. We're taking liquidity tokens that we previously were given in exchange for liquidity in a pool, and we're redeeming them, right? So
Hmm.
yeah, that's all basic, you know,
You give
Uniswap.
some, you get some.
Yeah.
Yeah.
But let's just look at like add liquidity. So we, as a user making a transaction, we select a specific pool and we say, here's how much of token A, here's how much of token B we're going to give. Um, so the contract finds the pool, right? Husks the data, which is what Marcus said earlier. We're taking a type, an item, a source, and a holder, and we're just saying assert that this item has data inside of it in its noun of this type, and assert that it's got this source and this holder. Now you can leave these empty if you want. That's why they're units.
Hmm.
So yeah, we assert that like the tokens that the user wants to deposit are correct for the pool, that they're like the actual tokens in the pool. We calculate how much liquidity they're earning, right, by the amount that they deposit. That's this formula here. Um, Sort of, you know, simple math, but like complex in semantics. So yeah, just take
Hmm.
that for what it is. So then we just add the amounts to the pool and then we mint the liquidity. So we end up with three side effects, right? Well, we end up with one side effect from us and three continuation calls, right? Our side effect is we modify our pool and then we say, okay, take token A, take token B, and mint more liquidity to the caller. Simple enough.
Hmm.
Same thing with remove liquidity. We do the calculations in reverse, and then we take the liquidity shares and we give the token A and we give the token B, right? Because they get a calculated blend of each token. Um,
Very nice.
yeah, yeah. So
Yeah.
that's the contract. Um, we don't. This is commented out because this is like Treasury protocol fee stuff that isn't really that useful. Yeah,
What about the read arm? For example, like
yeah,
this contract in its current implementation only does swaps between direct pools. I mean, similar to Uniswap. But
right.
Uniswap also has a router function that basically like calculates through read calls like a path to and from some pool. Um,
Right. So that's something that we could add. So
mhm.
yeah, so like right now the AMM contract does not offer any reads, but something that would be really convenient, yeah, would be a routing read, which would tell us if I want to swap, you know, X token for Y token, how do I do that? Because there's not a pool from X to Y or from Y to X. Well, we could read, you could do a call and say give me a route from X to Y, and we could return, okay, to go from X to Y, go from X to Z and then Z to Y, and we could return that as a
Mhm.
path. That would be really cool. We should do that.
That's
Yeah,
a good idea.
yeah.
And also this was like you see how the contracts are like structured and it's kind of nice and hoonish and urbity.
Mm-hmm.
But like like this is the simplest form of like swaps that we have. They're cool and like kind of robust, but like this is the simplest form. And the whole like the cooler parts maybe in some way come in when you do all this, like you get to do all the stuff that you have and that you can do in a unified computing environment
Mm-hmm.
without doing it all on chain. So like, I don't know, some exchange lodges like their peer-to-peer like swap thing. You can imagine how that's like very doable here. Kind of like bids and
Yes.
asks, and you just post them to your friends or through a router, or kind of just like federate them to everybody, or
Yeah.
like an order book or something else, like stuff that you don't want to necessarily put on chain, or you do want to put on chain, like the poker thing where you just deploy an escrow contract immediately with you and your buddy or who's playing as the ad basically holders. Um, there's a lot of moving parts that integrate these contracts in a cool
Yeah.
way.
Yeah, absolutely. So that sets us up well to talk about what's coming next. If this video was helpful, we'll definitely be making more. I think episode 2, we can go over the Gall app that interfaces with this
Mm.
contract for you that Marcus wrote to basically use this contract, right? Sort of like a front end,
Hmm.
but a little more, right?
Sort of like a little bit like a contract, but not a contract. Just an app that you have
Yeah.
running on your computer all the time, so
Yep.
can maybe do stuff for you
Yep.
while you're not there.
Yep. Very powerful stuff. All right. Well,
Awesome.
we'll wrap it up here, and we'll publish this and see what the feedback is like, and maybe make more. All right.
All right.
All right. Later,
Cheers.
guys.
Thanks.